Hey, today we will talk about convex hulls. In the previous chapters, we briefly talk about what is a convex hull. If you remember, in the plane in 2D, actually convex hulls, we said that if you have, let's say, some number of sides, and if you want to determine the convex hull of it, then we said that assume you have a kind of a rubber, and you put that rubber around your sides, and then once you release this rubber, it will cover the outer of these pins, and the resulting shape will actually be the convex hull of these given sets. For instance, if you assume such a rubber that will cover all these sides and with such a polygon. As you see, it's not passing through this side, since it's inside the region. If it passes through it, then it will be a concave shape, not a convex one. So in this chapter, we are trying to determine the convex hull of the given size. And for that, we have some algorithms. We'll be going through them in this brief chapter. So let's start with an example, and we have kind of an analogy between oil wells. It's a kind of a well where you actually try to get some oil. And as you know, in oils, we have several items, several components. Assume you have, for instance, components A, B, and C, D. And in each well, you have first well, let's say, this is one of your well, this is your second oil well, and all of these, you cannot have always same amount of same percentage of these components, and they always vary between the sources or between the wells. For instance, assume that right now we are only interested in a single, let's say, not a single, but two components, A and B, and we have two oil wells. In the first oil well, once you do actually obtaining these components from the well, you obtain 10% of component A, 30%, 35% of component B. But in the second mixture or second oil well, you obtain 16% of A and 20% of B. So these are two separate oil wells. In the first one, we have 35, let's say, percent of B. In the second, it's not as high as the first one. It is much less. It's 20% of the oils inside the second oil well is component B. So what now? The question is, can we obtain a kind of a special mixture in which we have 12% of A and 30% of B? So can we obtain a mixture, such a mixture, by using the first and the second oil wells to obtain such a specific ratio, 12 for A and 30 for B? So now let's go back to our previous observations. We said that in the first oil well, the mixture has actually the 10% of the mixture is A, 35% is B, but in the second, 16% is A and 20% is B. But the question is, can we obtain 12% of A, and I forgot what was the value for B, it's 30. So 12 for A and 30 for B. So is it possible to have a kind of a mixture in which we have 12% of A component and 30% of B component? So how can we obtain this mixture? Which amount should we have? So we can, is it possible to mix these two oil wells, and then the new mixture will have such a percentage for A and 30% of B? Is it possible? We say that this is possible since if you have the ratio 2:1, which means that you have 2 units of first, let's say, mixture and 1 unit of the second mixture in the previous slide. If you have such a mixture in the result, then your overall mixture, the resulting mixture, will have 12% of A and 30% of B. This is easily obtained. But what about a different mixture? Can we have a new mixture having 13% of A and 22% of B? And obviously, it's not possible if you just have two oil wells. We have one oil well here, let's say, and the other one here, and we have different A and B components inside, in between these two different oil wells. We said that the first one is okay, but the second one is not possible. This is since we just have two oil wells, we cannot obtain such a specific, let's say, percentage of A and B. But what about if you have three oil wells? They have, again, the third one has this time 7% of A and 15% of B. We say that, yes, this is okay, since if you have 1 unit of the first mixture, 1 unit from first oil well, 3 units from the second oil well, and just a single unit from the third oil well, and mix all these units together, mix all these oils together, we can obtain 13% of A and 22% of B. This is possible. But what is it? How this problem is actually related to convexity or convex hulls? Why we spend some time on this discussion? The thing is that if you have a kind of an actually triangle, and the vertices of the triangles are representing each oil valve. This is the first one. I think this should be the third one, and this is the second one as far as I remember. Assume that this is kind of an 2D plot, and x-axis is representing component A, and y-axis is representing component B. So if you have a kind of a triangle, and if your desired value, this is a desired value, we want to have 13% of A and 22% of B. So if you see that this desired value is inside the triangle, then yes, you can say that this mixture can be obtained by mixing some oils, some amount of oils from these three oil wells. But if you have a kind of an, let's say, percentage here outside of this, let's say, triangle, we can clearly say that it's not possible. We cannot obtain that mixture. And that is actually this valid region is the convex hull of the given oil wells. So this is how we relate convex hull to our previous problem. If your desired percentage is inside this convex hull, then yes, you can obtain such a mixture. But if it's outside the convex hull, then I can say that it's not possible. You cannot obtain that product. Let me make sure that the numbers. So the third mixture is 7% and 15% of B. So okay, this is the, I'm sorry, this should be the third oil well, the new oil well, and I think this is the first and the second one. And this desired value, if you remember, this was the first question we asked, 12% of A, and we want to have 30% of B. As you see, it is on the triangle. It is on, actually not on the triangle, it's on the line. Since at the beginning of the problem, we have these two oil wells. And as you see, if you have just two oil wells, then you can form a line between these oil wells. And if your desired value is on this line, then yes, you can say that by having some amount of oil from the first one and some amount from the second one, you can obtain such a mixture. But in order to have this value, these percentages, then you need to have another oil well. This is the third one. So this is how we can work with convex hulls if your desired value is inside the convex hull of these oil wells, then it's possible, but if it's outside, then we can say that we cannot obtain the resulting percentages. So let's have a look at the formal definition of convexity. What is convex hull? And we call a kind of any shape as a convex shape if and only if there are some points P and Q which are inside this set subset S, and this a line which is connecting these 2 points is completely inside the subset S. If that's the case, then we can say that the given subset S is a convex one. For instance, if you look at here, this line connecting P and Q is completely inside the subset, but if you look at a concave shape here, which is not convex, the line connecting P and Q together, some part of this line is outside this subset S. So I can say that this is not convex, but any line inside this convex shape is always inside the subset S. So we can say that it's an convex shape. So the convex hull actually we represent it with CH of S. The convex hull of subset S of a set S is the smallest convex set that contains S. Yes, we can have, for instance, if I draw such a shape, it's still convex and it's still containing this smallest region. I can also draw another one here, for instance. But the thing is that we are looking for the smallest convex set which is containing the given set S. And the given set S is this gray region. And the gray region itself is the convex hull. The outer boundary of this region is the convex hull, since all the lines inside this region is all completely contained in S. Any point, actually any line connecting any point sets inside this region is completely in the subset S. If that's the case, then you can say that the outer boundary of that subset S is actually the convex hull of the given set S. We can also say that it's also the intersection of any other convex regions. So this is actually the thing I mentioned at the beginning of this chapter. If you think about an elastic rubber band and assume that these sides are kind of nails on your 2D plane, and then if you release that rubber, actually it will snap around the nails and try to minimize its length. And as you see, we have a kind of a polygon, and this is obviously a convex polygon, and the outer boundary is the convex hull of the given set, let's say S. So what is the meaning of actually computation of this convex hull? What do we mean by the computation? So you'll be given a set P. In that set, you'll have some number of points, n number of points. And if you compute the convex hull of the given set, then that means you try to obtain the vertices on the convex hull in the clockwise order. So these are important. The output of your computation should be in the clockwise order, and your output point should be defining the convex hull in the clockwise order. Here's the example. For instance, we have 9 points. So your set has actually 9 sides. And then if you look at the result, the convex hull of this set P is represented with just 5 points. The thing is that, as we mentioned, they should be ordered, and in their order should be in clockwise. Let's have a look at it. It starts from 4, 5, 8, 2, 9, and then obviously go back to 4 to obtain the convex hull of the given set P. So how we are going to do the computation? So we need to actually have some kind of directed edges. Here you see an example on the right hand side. We have a direct edge between P and Q. So if your direct edge is actually on the convex hull, and I know that the edge between P and Q is on the convex hull of this given set. And if you look at this direct edge, this is moving in that direction to the right. And I can say that the points actually are always on the right-hand side of this direct edge, right? So if I draw another, let's say, direct edge, let's make it a bit thicker. Assume that this is another direct edge. Let's name this as L and M. From L to M, this is a direct edge, and it's going in again clockwise direction. And again, if you look at it, all the sides on this plane are on the right hand side of this direct edge. And if you look at other one here, assume that this is another direct edge, which is on the convex hull. If that's the case, again, the sides on this plane should be all on the right hand side of this directed edge. So if you can somehow find these direct edges where all your actually sides are always on the right hand side of your direct edge, then you are done. The only thing you need to do is to order all these so that you will have a clockwise convex hull. So this is how we do the computation. But this is obviously not an actually wise way. This is a bit slower, so that's why the algorithm is called as slow convex hull. So how we start? We start with number of points in the plane. We have some n number of points, and then the output is actually the list L, which has the vertices in the clockwise order, and that list will be representing the convex hull of the given set P. So in the algorithm, we need to have a list which is an empty list at the beginning, and then what we do for all the ordered pairs. So we have many pairs. So this is for instance, an ordered pair, and also we need to have the reverse of it. This is another ordered pair. So we don't know whether the sides are on the left or right. So we need to have all the ordered pairs of P times P, let's say, set. And obviously, P shouldn't be equal to Q. Otherwise, we cannot draw a line that will be a point. So then what we do, we have a condition for valid. This is a Boolean value. If it's true, we continue doing these operations. What are these operations? We take actually a kind of a direct edge, and then we check whether the remaining points, which are actually all the points inside this actually set P, is on the left hand side or on the right hand side of it. If it's on the left hand side, then we say that this valid is false. This is not the actually edge we are looking for, so you shouldn't do any more computation for that direct edge. You should stop that computation and continue with another direct edge. But if all the points are lies on the right hand side, then your valid is still true. You can add this edge to your output list, which is right now E, and you do all these computation for all the pairs you create actually at this point, at this statement. Which means that after you are done with for loop, then that means you have obtained all the direct edges on the convex hull of the given set P. If that's the case, then the only thing you need to do is to actually order these actually edges inside your data structure E, so that you will have proper clockwise polygon. If you do this computation, then that means you are done. Your output L will be actually the convex hull we are looking for.